always helpful and provides the technical support for these webinars. I'm John Pattison Williams. I think I know most of you on the call, but really thankful you're able to make it this morning, and we're looking forward to this presentation. We'll just make a note that it will be recorded this morning, so just so you're aware of that. And it will be posted to the PHJV YouTube channel shortly after the presentation. So it's my privilege to introduce Dr. Irena Creed this morning from the professor at the University of Toronto. And Irena, I think, will be well known to many of us in this community around wetland conservation and biophysical elements of carbon capture. And we're really excited to hear this talk this morning on wetlands as natural climate solutions and quantifying carbon capture potential while building a stronger, greener economy. Thank you, Irena, for your time today, and please take it away.
Thanks so much, John, for the warm introduction and the opportunity to talk to you today about some of the work that we're leading across Canada. John has asked me to speak about some of the wetland network work that we're doing, and I just wanted to, first of all, share with you what those projects are. We've been funded on 3 separate opportunities offered by Environment and Climate Change Canada. The first one is the foundational one on wetlands as nature-based solutions. But we've also been benefited from 2 extension projects that really look at the socioeconomic part of wetlands as nature-based solutions. The first one was on Lake Winnipeg, and John is a lead on that proposal. And the second one is being led by Roy Brower and others on the Great Lakes St. Lawrence Basin. So this project is one that goes from coast to coast of Canada, predominantly on agricultural landscapes. We've built a remarkable team of expertise. The institutions are shown here, again, going from UBC to Sherbrooke and beyond. We've had the privilege of having international experts guide us, including Shil Bansal from the USGS and Kevin Bishop from the Swedish University of Agricultural Sciences, and of course, Tim Moore from McGill University, who is Professor Emeritus. And so without them, I would not be able to present this work, and I just want to acknowledge them collectively, and in particular, the privilege that I have to co-lead this work with Pascal Badeau from Ducks Unlimited Canada. So just trying to start from the beginning, we all know that our climate is changing, and the concentration of greenhouse gases in the atmosphere are increasing, resulting in a warming of temperature. This is the iconic hockey stick image, which shows the red zone of at least in times relevant to human civilization, changes in temperature that have been unprecedented. And so many nations are aware of this and have taken action, and the Paris Agreement is a legally binding international treaty on climate change, where 196 parties at the UN Climate Change Conference, COP21 in Paris, was agreed to and entered into force in 2016. Now, the Paris Agreement sets the goal of a global mean temperature increase of 1.5 degrees Celsius by 2100. And this latest report shows that in 2023, we reached 1.3 degrees Celsius. So based on all of the current policies and actions, we are heading for a 2.7 degrees Celsius warming. And the most optimistic scenario, which assumes full implementation of all announced targets, is 1.8 degrees Celsius warming. So I think we can all agree that more work needs to be done. Now, there is these various devices for tracking the progress of individual countries in their climate change performance. And so I just wanted to share with you, this one is just recently from 2024. You could see that of the nations participating, Denmark is the highest ranked country in the world. But in contrast, Canada is ranked number 62. And just to show that we're in the company that we keep, Saudi Arabia is ranked at 67. And so my point in showing you this slide is to say that work needs to be done, but some countries have more work to do than others. And so I want to talk about natural climate solutions as an opportunity for us to take those actions. And just to give you a definition, natural climate solutions are actions to protect, conserve, and restore nature in order to store carbon and reduce greenhouse gas emissions. Now, a lot of people are using a lot of words that are very similar: nature-based solutions, nature-based climate solutions, natural climate solutions. And so thankfully, there has been some work done recently and published in Nature that talks about the principles of natural climate solutions. And in this case, we see that there's an outer ring of the circle, and then there are spokes. So it's kind of like a hub and spoke model. The foundational principles are on the outer edge of the wheel, and that basically says for natural climate solutions, they need to be nature-based, they need to be sustainable, they need to be additional, they need to be measurable, and they need to be equitable. And some of the operational principles to achieve those foundational principles are outlined in the spokes. And I'm not going to go into detail on all of them, but except one. The role of our team is to show that natural climate solutions can be measurable. And so what we're predominantly focused on is to look at how we can avoid double accounting, report uncertainty, account conservatively, and use CO2 equivalent metrics in order to assess natural climate solutions. So scientists estimate, and this is the good news story, that nature could pull 10 gigatons, that's 10 billion metric tons of carbon from the atmosphere. And this represents more than a third of the greenhouse gas reductions needed by 2030 to keep the global temperature increases under 2 degrees Celsius. This includes about 5 gigatons in avoided sources. And what that means is the protection of lands, of intact lands. And it also includes about 5 gigatons in enhanced sinks. So natural climate solutions can include forest, wetlands, and grasslands, among other things. And some are looking at the oceans, for example. But our focus today is on wetlands. And so collectively, this National Wetland Research Network has 5 objectives, and I'm going to share with you some of the ideas and some of the progress under each one of them. The first one is to develop authoritative estimates of landscape scale density of wetland coverage for agricultural landscapes. And so first of all, just a basic definition of what is a wetland. And if you were to go to the Oxford Dictionary, you would see something like wetlands are areas of land where water covers the soil all year or just at certain times of the year. Now, when we go to the IPCC, it also provides official definitions, but invites each country to adapt them based on their specific circumstances. And so as we start this project, a seemingly innocent question turned out to be a very complicated one. What is the wetland? What is its boundary? And so when you see this cartoon on the left and an air photo on the right, should it include the open water, the emergent vegetation, the wet meadow zone, as well as the riparian area surrounding that? And so right now, there is not a consensus of what defines the wetland, but when we think about what the carbon implications are and the greenhouse gas emissions, it matters. For example, do we account for the carbon stored in riparian areas or only in the open water? So these are things that we want to keep in mind. Thankfully, we have so many emerging technologies, and in this case, looking at satellites, to help us map the different components of the wetland. So we are able to look at the open water, the emergent vegetation, the wet meadow, and riparian area, and to be able to account for these different components of a wetland in terms of their role as a natural climate solution. I just want to share with you some of the work that the Research Network has done in terms of mapping wetlands. We want to have a standardized metric for what is a wetland, and so we opted to look at Landsat thematic mapper data with a 30-meter resolution. And we started covering it over from 1984 to present. So we have almost a 40-year record of that wet area on top of the soil. And so some of the questions then become, using these remote sensing techniques, should the definition consider the potential expansion versus contraction of open water in the wetlands? And we have been looking at tools to not only map it, but to be able to show the probability of inundation within wetlands in the database that we have created. And by the way, we have completed that for the entire Lake Winnipeg watershed and are currently working on completing that for the Great Lakes St. Lawrence Basin as well. Other things is to think about wetlands not just individually, but collectively, and the hydrologic connectivity, but also the biological connectivity between them. And so we're now moving beyond just individual wetlands, but to look at things like wetlandscapes and looking at at least initially, the hydrologic connection among these different wetlands, as the inflows into and out of wetlands in terms of carbon will be important. I just want to show you that this is some of the data that we have generated for the Lake Winnipeg watershed. And whereas we might be thinking based on our experience of climate change, the wetland number and size and the wetland to wetland connectivity has actually increased quite a bit in the Lake Winnipeg watershed from 1984 to a peak of about 2011. And now it seems to be stabilizing. I think this reflects the change in the climate regime in the Prairie pothole region. Or else we're going through some long natural cycle of the climate in this area. The second objective was to develop authoritative estimates for rates of organic carbon accumulation, as well as the greenhouse gas fluxes to the atmosphere. So we thought that we would have a lot of data to start, foundational data. We went through a literature review and found over 100 articles. But what we found was that the actual database is, I hate to say it, but relatively weak. And so a large effort of our research network is to build that database on carbon storage within wetlands, as well as greenhouse gas fluxes into and out of those wetlands. And so we've been building a lot of instrumentation in the field. We have a whole series of flux towers that have gone up and are continuing to be expanded in different parts of Canada. We have a lot of measurements happening within the wetlands across, again, from coast to coast of Canada in the agricultural landscapes. And for some fewer, we have ones that we've actually gone out to, collected cores, and started dating the cores so that we can look at carbon sequestration rates. And so collectively, we have about 80 core sites, 8 eddy covariance flux towers, and about 150 wetlands where measurements are being taken. Unfortunately, our project is still relatively new, and we're probably in our third year. And so we have some of the data is only 1 or 2 years in terms of length. But it's a really important initiative that we are undertaking. I took some effort to see what other places in the world have in terms of data to help support what we're doing in Canada, and in particular working in Fennoscandia, so that's Norway, Sweden, and Finland. And yet there too, the data on carbon sequestration and greenhouse gases is just starting to be captured. And so it's really important when we talk about natural climate solutions and remember some of the foundational principles are that they are measurable and that we can reduce uncertainty. We're still in the early stages of being able to do that. The third objective was to develop these robust estimates of process controls on organic carbon accumulation and greenhouse gases. And I just want to start by saying that the data that I'm going to show you today is really focusing on the organic carbon accumulation, but we have just recently started to be able to come up with those estimates for the greenhouse gas flux models, which hopefully I'll come back and share with you at another time. So we know that wetlands are important carbon reactors. They store carbon, but they also emit carbon. And when you look at a very simple wetland carbon cycle, a lot of excitement about wetlands as natural climate solutions is with the CO2 being captured within the wetlands. But recently, there's been a lot of discussion in the media as well as the scientific community that wetlands may actually be posing a problem for climate. There is this recent flux of scientific articles that are talking about the big methane pulse that is happening in the northern hemisphere, and a lot of the people believe it's attributed to the wetlands. And so we're a bit concerned and we're aware, and we need to understand the potential trade-offs of putting wetlands and restoring them for the carbon benefits when we can sequester CO2, but we might have the unintended consequences of emitting more methane. And why does that matter? Because we know that CO2 has global warming potential of, it's according to the way the IPCC does it, of 1 over a 100-year period, but methane has 25 times that global warming potential. And so it's not a 1-for-1. We have to really be careful about introducing more methane into the atmosphere. Of course, nitrous oxide is even more at 298 times the global warming potential. But we have not observed very much nitrous oxide emissions from the wetlands in the Prairie Pothole region. So we're really focusing on the CO2 and the methane. And so I told you that we went and compiled as much literature as we could, and I'm going to show you some of the results of that for the inland intact wetlands here. Now, just to navigate it, most of the data comes from the southern part of Canada and the northern part of the United States. There are many more studies that are tidal or coastal wetlands, and ones that are in swamps, but we really focused it on marshes. And so I just want to explain that that is the data I'm presenting today. And if you look on the right-hand side, there are 2 plots, and on the y-axis, it's an intact wetland, which we considered like an intact protected wetland, a natural wetland. Then we go to the drained wetland and then the restored wetland, and that repeats on the top and the bottom plots. So when we look at carbon dioxide flux, we see that intact wetlands, it's a sink. Drained wetlands, it's a source for CO2, and restored wetlands is a sink. And so good news there, wetlands that are protected and intact or restored are actually removing the CO2. When we look at the methane, all 3 are emitting some methane, and you can see that we categorized it into low versus high methane emitters. And for 76 to 80% of the wetlands, they emit very low levels of methane. So that's a good news, at least for this part of the world, that the marsh wetlands that are there, the vast majority of them emit a small amount of methane. There are some that emit what we consider high levels, and you can see them in the orange dots on the map. And of course, we're going to be investigating what might be contributing to that in our work. Now, when we talk about the difference of the global warming potential of CO2 and methane, and when it's captured in the global warming potential, some scientists believe that methane gets an unfair spotlight on it, an unfair spotlight on it, and in part because it's a very short-lived gas versus CO2, which is a longer-lived gas. And so recently, there's been some discussion about should we be investigating what global warming potential metric that we actually use. And so I just want to introduce a relatively new one, which is called the Global Warming Potential Star. And I'm just going to go through it, and I've highlighted what I want you to focus in on this slide. So for the global warming potential, the definition is the amount of energy 1 ton of a gas absorbs in the atmosphere relative to CO2 over a specific period of time. The pros of this metric is that it's easy to implement, and it is the standard for expressing CO2 equivalent emissions. But the cons are that it de-emphasizes the effects of short-lived gases such as methane. And so scientists introduced the global warming potential star, and that one looks at the amount of energy a step change emission of a gas absorbs in the atmosphere. And so you can imagine that if you're on the landscape and you're actually converting a wetland from drained to restored or restored to drained, we can look at that as a relative pulse emission of CO2 over a specific time. And the pros are this is much more accurate representation because it compares a step change of a short-lived gas to a pulse of CO2. And it's designed to be easily implementable into current policy. The cons are it relies on the GWP values and it's applicable only for the short-lived gases. Therefore, we would have to, if we were to introduce this into national greenhouse gas reporting, you'd have to report both on the global warming potential as well as the global warming potential star. So we just wanted to explore this in our research and to see what the implications could be for marsh-like wetlands that predominate on the prairie pothole region. And so we developed the models and we looked at the effects of wetland conversion on both gases. And on the three different scenarios, a wetland to wetland is basically we created a wetland and then for 50 years later, what is the impact of that created wetland? Then the wetland to a drained state, and the third scenario is drained to restored. And so on the right-hand side, you could see on the far right-hand side, you could see what it would be if it was just the global warming potential. And under the natural one, you see that low ones, the green line is showing low methane emissions. And as soon as it's created, it's having a positive carbon benefit. When you look at the red line, you see a linear line that shows that you're actually not having that carbon benefit. It is introducing greenhouse gases that have that net warming effect. However, when you think about natural wetlands, this is the scale of 500 years. And natural wetlands, if they've been on the landscape for 1,000 years, you can imagine that perhaps that high level would eventually drop. If you look again, staying on the far right side, the wetland to the drained, they're almost the same. And if you look at the drained to the restored, you see a little bit of an increase and then the sink function that comes in. So what did the global water potential star introduce? If we can now go to the plot next to that, you'll see, first of all, that in the created wetland and 50 years later, we are able to pick up that initial pulse of methane, and then we see it flatten out over the long term. So that rate of increase isn't as long for those wetlands that produce a lot of methane. In contrast, those that are low emitters show the same kind of continuous decline. When we look at the wetland to the drain state, we can see that we're able to capture a net sink or reduction in methane, which is because the water's now gone. You've changed the oxygen conditions, but then you can see that that can go up over time. And since had no data for restored wetlands that were high methane emitters, we were not able to show that scenario. And so the one thing it's a bit complicated. It shows that there's nuances by using the GWP star metric, but the key message is that it takes about 100 years for wetlands in either scenario to start providing the carbon benefit. And so we need to protect those wetlands that are on the landscape that are currently functioning as sink. And if we should be doing restoration, but it is not going to help us alone meet the 2030 target of reduction of greenhouse gases in the atmosphere. This is a longer term and at least 100 years out of a climate benefit. So with that kind of context, I now want to talk about the two approaches of natural climate solutions, and the first one being protecting nature. And protecting wetlands can avoid the release of greenhouse gases, but we want to know how can we estimate the actual carbon sequestration potential in these intact wetlands. And so, as I mentioned, we did go out to about 80 wetlands. We took the sediment cores, we dated them, and we actually calculated the carbon sequestration rates. And what you see here is it's a highly variable organic carbon sequestration rate. The mean is about 0.68 megagrams per hectare per year, large standard deviation. And so when we look at trying to estimate that for the millions of wetlands that occur in Canada, how can we predict what it would be and then include that, for example, in a national greenhouse gas inventory report? And so we got together and a number of experts and started thinking about what are the state factors that influence the wetland carbon cycle, what are the interactive controls, the indirect controls, and then the direct controls. And for those of you who are soil scientists, the state factors are really coming from Jenny from 1941 and his work on what controls soil forming practices. And the interactive controls and indirect controls are inspired by examples of Stuart Chapin in ecosystem ecology about how to look at how these various factors interact to affect a certain response. And in this case, we introduced it for the wetland carbon cycle. So we have assessed that the direct controls include carbon quantity, the carbon quality, which is basically whether it's labile versus refractory carbon, and it could be estimated by the carbon to nitrogen ratio, the bulk density of the soil, the cation exchange capacity of the soil, the aggregate reactivity, the oxygen concentration and redox potential, and the temperature. But what Hans did not introduce in 1941, and that was because it was 20 years before we officially observed the era of the Anthropocene, which is around 1963, is the effect of human activity. And so we know that humans have effects by cropping systems, tillage, livestock, fertilizer, manure, contributing to wind and runoff erosion, drainage and restoration, and salt application. And so these obviously have a huge effect on the indirect controls and the direct controls that in turn affect wetland carbon cycle. So by looking at these two images, you can see the complexity of what we're looking at. And so now we have to know, how do we develop models that can actually predict that carbon sequestration rate? And so we're benefiting so much from the era of artificial intelligence that can aid us in predicting the wetland carbon sequestration rates. And basically, it takes all the inputs and you get an output, and the artificial intelligence is using all these different algorithms to look at all the potential interactions, interdependencies of these various controls. And so I just want to share with you some of the work that we have done most recently. The RF is the random forest artificial intelligence model. And we wanted to look at what was easy to measure, what could be measured by remote sensing, or what do national governments have in terms of properties of those direct controls. And so we identified a human impact index, which we could derive from a national government inventory, the integrated normalized difference vegetation index, which is our proxy for carbon quantity, the inundation probability from Landsat imagery that would look at the proxy for oxygen condition and the redox potential, the land surface temperature, and again, from the national databases, the bulk density, cation exchange, sand content, and clay content. And so for those of you who are familiar with random forests, what it gives you is a ranking of the importance of various variables. And then if you look at the partial dependency plots, it tells you what the nature of that relationship is. And the really cool thing is you can see that the model can use data that is not necessarily linear relationships. And you can see on the partial dependency that many of these are not linear relationships. But what comes out is that the human impact index is the #1 control of carbon sequestration rates in these intact wetlands. Beyond that were the sand, clay, bulk density, and then the inundation probability, cation exchange capacity, the integrated normalized difference vegetation index, and finally, the land surface temperature. When we look at putting that into a predictive model, we can now see that we can actually predict with relatively high confidence about over 90% of the variance in the carbon sequestration rates. The slope is not a 1, which would be the predicted and observed are matching 1-to-1. There's still some uncertainty of what we're not capturing, but it's close to 1 at about 0.9. And so we're continuing this work. And as I mentioned, we have just recently started doing this work for the greenhouse gases for CO2 and methane. And so far, looks like we're also able to achieve relatively good predictions for these individual wetlands. So that's the work that we're doing in terms of protecting the wetlands that are there. Now, I want to talk about the rewetting, and I want to talk about what happens when we take the degraded and drained wetlands and re-wet them, and what the implications are from them shifting from carbon sources to sinks. And also if we can actually estimate the carbon sequestration potential in restored wetlands. Now, why are we really interested in this? And as I mentioned at the beginning of the slide deck, there's a lot of interest in natural climate solutions, and there's a lot of big money being invested in these wetlands. And Canada's investment is supported through Bill C-12, which supports Canada's efforts to achieve net zero greenhouse gas emissions by the year 2050. It made 10-year fiscal commitments of about $3.2 billion in terms of planting 2 billion trees, 631 million to protect and restore grasslands and wetlands, and 98 million to establish a new climate solutions for agricultural fund. So a lot of money invested in restoring these landscapes, in this case, forests, grasslands, and wetlands. But the question becomes, how much do we really know about the climate benefits of these restored natural settings? So whether it's forest grasslands or in this case, wetlands, we actually have very little data to support a lot of these investments. And so to help answer that question, we established chronosequences of restored wetlands to monitor the changes in the rates of carbon sequestration with restoration age. We were able to benefit from the long history of work of Ducks Unlimited in terms of restoring wetlands. We were able to focus on wetlands that were drained 15-year-old since restoration, 25, 40 years since restoration, and intact wetlands. This photo series is based on the Tim Horton camp and in Onondaga, and you can see the types of changes to the wetlands and surroundings as a result of the restoration. We focused on things that were easy to restore. So these were relatively small wetlands at 0.5, less than 0.5 hectares. They did not have hydrologic inflows or outflows. Some people refer to them as geographically isolated wetlands. They were drained by a drainage ditch, and it could be simply restored by plugging that ditch. And so we went to these wetlands and we collected the cores, and we used lead-210 and cesium-137 radioisotope dating to estimate the annual organic carbon sequestration rates. And excited to show you some of the results. This is a plot of the cumulative organic carbon stock since restoration. And so you can see, and we would all predict, you plug the ditch and the wetland is going to start accumulating carbon. But we also wanted to look at the rate of carbon sequestration, and this one reveals even more interesting finding. When we plot the change in organic carbon stock since restoration, we can see that the rate increases up to about 10 years, and then it starts to decrease. And then after 20 years, you see that the change in stock in the rate is at zero. So it basically functions as if it was an intact wetland. And so to try to understand the upswing and the downswing of this plot, we're posing some theories, and the ideas is shown to you on the bottom, that intact wetlands may be nutrient limited and may have a relatively low accumulation of the organic carbon stock. When you're drained, it becomes water limited, so you again have a low accumulation of the organic carbon stock. Early restoration, it's neither nutrient or water limited. You get an increasing accumulation of the stock. Late restored, nutrients start to become limited. You get a decrease in that stock. And then finally, you're back to the equilibrium of an intact wetland, nutrient limited and relatively low accumulation of organic carbon stock. This kind of insight shows that we might be able to maybe manipulate this curve. If we understand that it's nutrient limited and we want to store more carbon, we might add nutrient amendments, for example, to enable higher capture of carbon. And we can also explore the edges around the wetland too to see how we can maximize some of the carbon sequestration. So we've talked about the field-based measurements and doing a lot of the things on the protected wetlands and the restored wetlands. Now I want to share with you some of the early ideas because we haven't advanced that far in our network work yet on modeling the carbon benefits of wetlands and how can we predict the change in carbon status as wetlands go from intact to drained to restored. And so this is where we're starting to look at areas outside of Canada since we don't have that data yet. And we want to be able to explore it first where we do have data and then apply our learnings to the Canadian network that we are establishing and starting to collect data from. And so colleagues in Sweden have sites that have all the data that we need for at least 2 years of record that include an intact wetland near a drained wetland, near a restored wetland. And we're sharing all of that data to build models. And this is a photo of Betty, who's going to be a postdoc working with us in terms of developing some of those models, process-based models of carbon dynamics and intact to drain to restored wetlands. But one of the things that we're also interested in is the wetlandscape. And as I mentioned earlier, wetlands are not islands, and they have connections not only to each other, but to the drainage network. And so work that we're doing with Ali Amelie from the University of British Columbia is to build models to simulate these wetlandscapes. He's leading the work on identifying static and dynamic hydrologic connection of wetlands for entire North America. And then he'll be developing scenario analysis tools to look at the effect of draining and restoring these hydrologic connections. I'm interested in adding on to that the carbon inflows and outflows. And of course, data is not that easily accessible. So if anybody has ideas of where we can get some of the carbon data to build the models, I would love to hear from you after this presentation. And so we want to create, contribute to policies and create tools that help policymakers and managers. And so our vision is to be able to develop a wetland carbon tracker and calculator. And again, based on those operational principles of measurable under natural climate solutions, we want to avoid the double counting. And in particular, when you think about it, carbon moving from upslope to the wetland or moving out of that wetland and downslope. We want to make sure that we're not counting it double in its journey. We want to be able to explicitly report the uncertainty, account conservatively, use the CO2 equivalent metric showing the difference between global warming potential and the global warming potential star. And we want to make it generalizable and scalable so that we can go from a wetland in Alberta through to wetlands in Quebec, and that we can go from individual wetlands to wetlandscapes to entire watersheds. And of course, we want this calculator to be available to individual communities, industries, farmers, as well as governments. So I'm just sitting in an Edmonton hotel right now, had the pleasure of meeting people who are working in this space of being able to create these types of calculators. I'm pretty excited to be able to move that forward in a good way that I think is actually achievable in the remaining 2 years of our project. The fourth objective was to develop robust estimates of wetlands as nature-based solutions for carbon versus other benefits. And first of all, I want to share with you some data that we did. And John, thank you for participating in this project on the carbon markets. So with knowledge of the carbon sequestration rates, we wanted to explore how could we incentivize the protection and restoration of wetlands. And so we did a very simple analysis on the carbon market potential. We selected the mean carbon sequestration rate, and as you may recall, it was 0.68 megagrams carbon per hectare per year. We selected the 30-year time frame for sequestering organic carbon from 2021 to 2050 and chose that because of Canada's commitment to achieve net zero emissions by 2050. We determine the cost of restoring wetlands, and this is a highly variable cost depending upon where you are in Canada, depending upon the type of restoration that is needed. It's very different in the prairies than it would be, for example, in Ontario and Quebec. And it's also the real estate value of that land. And so I'm showing you the full range here. And finally, we calculate the benefit to cost ratio. And if that ratio is 1, it's break even. Basically, all the benefits you get from carbon are covered in the costs in terms of creating that wetland or restoring that wetland. And if it's greater than 1, then the wetland restoration project is justified based on carbon benefits alone. So I'm just going to show you the results of that and the 2 key findings that we had. The first finding is that it's better to protect rather than restore wetlands based on the carbon sequestration potential. And just going to the right side of this table, you see the benefit to cost ratio and the protection. Remember, if it's greater than 1, then it's justifiable based on the carbon sequestration potential alone. And so the key finding here is we really must incentivize landowners to maintain the remaining intact wetlands on their landscapes. If I go to the second finding, carbon benefits alone are not enough to incentivize the restoration of wetlands. Well, not enough everywhere. The range was high. It went from 0.26 to 1.20. So there's some places where the restoration would be justified based on carbon sequestration alone. But in many places it is not. And that means we must increase or stack other ecosystem benefits to create larger financial incentives. And so this is where I want to share that wetlands provide more ecosystems than just carbon. Because we're focused on natural climate solutions, I don't want to risk people becoming very myopic and focusing on carbon only. Wetlands provide many other ecosystem services. A lot of that information is starting to be pulled together. And again, working with colleagues in Sweden, we're conducting a major synthesis of the literature. It's literally thousands of papers pulled together, and we'll be looking at both the benefits and the potential harms of wetlands from many different ecosystem functions. And those functions include not only the greenhouse gases, but biodiversity, mercury, pests, nutrients, pathogens, the hydrology and recreation. And so we're doing this work now, and over the next year, we're producing a theory and practice paper, which is really targeted to the multiple benefits of wetlands from the theory and guidance for practitioners, a synthesis paper, and an opinion paper. But knowing that we want to be able to move from just desktop papers to on-the-ground applications, we are also looking at expanding that kind of carbon calculator to look at building a wetland ecosystem service tracker and calculator. Now, I've had the privilege of working with the government of Alberta and looking at tools to implement their wetland policy that was put into effect. And they look at it when they shift their policy from an area to a function-based policy. They needed to look at the various indicators of wetlands for the various functions that broadly included hydrologic health, water purification, and ecological health. carbon sequestration was not one of the functions in their wetland policy. We're now able to add that, and the idea would be to look at those four functions: hydrologic health, water purification, ecological health, and net carbon sequestration, and look at potential synergies and trade-offs among them and come up with scores of wetlands, an A, B, C, D grade, for example, for the functions that they produce. Now, I want to share with you how we might be doing it, and this is still pretty early days, but we've had the privilege of working with the city of Calgary, and this is now more of an urban landscape, of coming up with a wetland function tool. They call it the Aquatic Condition Index. And basically, we had advisory table coming up with lists of indicators. They really benefited from the approach that we used here and framed their analysis in a similar way. And then we went through a number of different approaches for combining those indicators, and that's what I want to share with you here. We had two phases, and one was having an optimization of the wetland function index through a sensitivity-driven reduction of indicators. When we started this work, even with working for the government of Alberta, we had well over 100 indicators. And frankly, that's not practical. And so one of the phase one of our work was to reduce the number of indicators using a sensitivity analysis. And we were successful in doing that. And a recent publication shows you the approach that we used of taking the massive number of indicators and reducing them into something that's more reasonable for application. But the second phase is one that I find even more interesting, is that we wanted to first shift that from field-based and desktop to a fully desktop tool. And we also wanted to explore the potential of using human and machines to look at the relationships. And so again, bringing in artificial intelligence in helping to build these models. And so what we found was that the desktop, we were able to easily reduce the field and desktop to just desktop. And secondly, that we found that a hybrid approach of using both human and machine gave us the best results. And here are some of those results. So again, this is based on the wetlands in the city of Calgary, and they were interested in the hydrologic, ecological, and water quality. We have the testing and training models below. And, when we think about it, our goal is to at least get 60% explanation of the variance for a tool to even be viable. In the machine-based approach solely, which was artificial intelligence, picked the indicators and looked at the relationships among them, we got 76, 70, and 43. Really tough on the water one. When we just did the experts, which is the way it's been traditionally done, it was 50%, 70, and 58%, actually did better in terms of the water quality. But when we combined the two together, so we had the experts come up with the list of the indicators and the machine telling us the relationships among them, we came up with the best performance overall. And so 63% hydrological, but 78% ecological and 63% water quality. And similarly, good performance both on the testing and training data sets. And so finally, I just want to share with you the fifth objective. And again, it is about developing policy and practice tools to incentivize the use of wetlands as nature-based solutions for multiple benefits in agricultural landscapes. And this is ongoing work. The first one is to create a repository to compile databases, protocols, information, guidelines that will be displayed in a public and openly accessible repository. We don't ever want anyone else interested in this work to have to go and, go to individual scientific papers to pull data out. We want to make this openly available to everyone. And so that's what our commitment is, and we will be generating a website where everybody can download these data freely. We also want to identify managed wetlands and work to get them included in the National Greenhouse Gas Inventory. Right now, wetlands are not part of the National Greenhouse Gas Inventory report. And just to be fair, they're not included in the United States either, and not included in many parts of the world. To be included, they have to be defined as managed wetlands, and we've been working with the federal government on what does managed wetlands actually mean and how we can get them included in the greenhouse gas inventory reports. We're also looking to estimating the agricultural impacts of wetland carbon storage and greenhouse gas emissions to enable individual farmers to make land management decisions that are consistent and quantifiable at the national scale. Here we're working with Ag and Agri-Food Canada and the Hollis model, which currently does not have wetlands integrated into it. And we're just advertising for a postdoc to help us do that in the coming next 2 years. And finally, the work that we will do will be shared with those who have designed the National Index on Agri-Food Sustainability. Hopefully, they will find the tools that we're generating useful in looking at that kind of certification of agri-food sustainability that is currently underway. And so just finally, it's just been a pleasure to be able to speak with you today. Anybody interested in following up on any aspect of this, I just want to share the email addresses for myself, but my co-lead Pascal Badeau as well. And at that, I will say thank you very much, John.
Thank you so much, Irena, for this presentation. And we'll give a virtual round of applause or do your little emoji thing. Say, well done. Thank you so much for your time. I think I'm always struck by the breadth and depth of the work that you do. And there is a lot packed into those 50 minutes. So my mind was trying to follow it all, and it was really impressive. But I'm sure many people have questions. Just to hear a little bit more. So if there are with hands, I see Graham, you have a question. Feel free.
That's great. Thank you very much. If you can hear me okay. I was intrigued with your purchase and management rights concept around the wetlands and other public ecosystem services. And I was a couple little questions. One is, since it's not a regulated off price, you got a lower price of between $6 and $12 US, so that might change your model a bit. But how are you going to delineate between the public land, i.e. the water and up to the high water mark, the private land, and the watershed, and in purchasing of those management rights, essentially to protect that space? And then the second question is, who pays? If you don't have a market instrument, then how are you going to generate the other half of the management agreement in order to fund the purchase of the management rights?
Well, thanks for those excellent questions. And right now, we don't have a carbon market for wetlands. But I think that if we build the case that we can actually quantify some of these things, that's a step in that direction. And I think your first question was, if I misremember, please let me know, but who owns the carbon that is actually being stored there, for example, in a protected wetland? If someone's managing it, do they get the compensation, or is it part of the government's? And I think that is, if I got that wrong, Graham, please let me know.
Well,
and so
right now, carbon is not a property right.
Yeah.
So you're dealing with essentially buying or selling a data. And in the backstop legislation, or here in Alberta, it's all not consistent. You've got to be the exclusive owner. So what it means in general terms is, if I'm a private landowner that goes up to the edge, I own certain parts, or at least you have control over it, but I don't have control, particularly in Alberta, because a wetland up into the change of zone is public land.
Yeah.
So the management agreement you want to put around it somewhat already exists in legislation, so you can't transact on it. And so you're having to transact on areas outside that, the wetland. So you're not buying and selling a credit or offset. That's why I'm using the word management agreement.
Yeah.
Is you're purchasing a set of rights that somebody can't do. So that's the conversation around how from the front end, what are you trying to bundle? And then the second of all, who's buying?
Yeah, so what we know is that what happens outside the wetland has a huge influence on what happens inside the wetland, whether it's intact or whether it's restored. And so I think that this is not in place right now, but part of our research is to provide evidence to what could influence policy. And if that were the case, then we would argue that certain management practices, and we've actually just recently completed a review of what some of those might be to enhance the carbon sequestration of those that are lands that are under the control of the government. And so it's kind of leading edge, and our work is only to try to influence in that regard, to illustrate and to track the carbon movement from the watershed to the riparian to the wetland and downstream, and how human activities on that landscape influence the amount that's stored in the wetlands. And that's a first step. And of course, when we also look at lands that are natural landscapes, and predominantly most of those are now on Indigenous landholders, should they benefit from protecting those wetland carbon stocks as well? And so we are looking, these are like new ideas, and we're just entering into this space, but that is where the conversation is going towards, Graham. We don't have all the answers now, but that is what people are in government are really interested in learning. That might inform future management arrangements as you describe them.
Well, I'll share with
Sure,
you before
thanks,
I shut up
Graham.
here, John. But I would say the
cut you off in
market
a
is here
moment
already.
Graham.
So
Yeah.
anyway, thank you, John.
I know Graham has lots of thoughts and good insights and experience on that. So we'll carry on that conversation on the side too. Just want to give a couple others a chance here. Chris from ECCC.
Hey, Irena, it's Chris Spence.
Hey, Chris.
Hey, great talk. I guess I'd like to go back to the beginning when you were talking about mapping what I think it was wetland area, Lake Winnipeg watershed, and I may have misunderstood, but it might have been that you documented an increase in wetland area across the watershed, and I found this interesting because almost everything that I'm aware of suggests that there's been, significant wetland loss across that watershed, particularly in southeastern Saskatchewan and Manitoba. And I'm wondering if I could get your thoughts on because of the methods you use. Are you measuring, because it's Landsat, are you just measuring more wet areas in the sense that there's been greater flooding and maybe not an increase in wetland area? Anyway, it's a comment, but I'd be curious about your thoughts about that.
Yeah, excellent question, Chris. And when we developed the Landsat-based estimates of wetlands, they were ground validated with wetland inventories, and those wetland inventories were based on catchments throughout the Prairie Pothole region, again provided by Ducks Unlimited Canada. And so we had very good confidence that we were able to predict wetlands that were on the ground. But your question is about, and I comment on that, what is a wetland and what is the boundary, because you do get an expansion and contraction based on inundated area. And so it gets down to the root is what is the definition of a wetland and what is it based, and yes, we know that there are definitions based on changes in the hydric properties of the soil and hydrophilic plants. But when you're trying to develop a tool for a nation to be able to capture wetlands in national greenhouse gas inventory reports, we don't have that data, right? So we're looking at satellite technology to assist with that data. And the question becomes, do you look at the potential of expansion and contraction, or do you look at the probability of it being inundated, which might be in terms of the original ground truth data that we had, we'd want to look at that. And of course, everything that we're talking about, we're living in a non-stationary world. Climates are changing, and in this area, the evidence is that it's some parts are becoming wetter, which is I was surprised by the result. But when you look at the data, those inundated areas are increasing and expanding, at least from 1984 or 1991 to 2011, and now it's starting to shift. And so we have to have those discussions collectively. It's not up to one person to make that decision about knowing that we want to include wetlands in the National Greenhouse Gas Inventory Report. How do we come up with a standardized approach that is reproducible, that is realistic and reasonable as well? And so we haven't delineated the boundaries, but those are the conversations that we need to have, Chris.
Great. Thank you
That's
for
great.
that
Yeah,
question,
thanks.
Chris. Yeah, thank you so much, and Irena, for your response. I know that we have come to time now, and I don't know, it's not always popular to be the facilitator when you have to end conversations, but please reach out to me if you have any other questions, or to Irena, or I can connect you with Irena. And we really look forward to the final results coming through in the next 2 years on this project. And thank you for your continuing work. All right, I hope you all have a wonderful afternoon, and great to see some faces. Stephen Carlisle's face just popped up. How nice. And we're really glad that somebody could come today, and wishing you a rest of the year. Have a good day. Okay, bye.